Okay. So 7.2, we're going to talk more about exponents. 7.3, 7.4, we're going to do the same thing. And 7.2, we'll talk about roots again, and we'll talk about them as a fractional exponent. So rational exponents, they've been defined in such a way as to make their property the same as the properties for the integer exponent. So we're going to have the same rules. In this section, we'll explore the meaning of a base raised to a rational or a fractional exponent. And then we'll also discover how we can use those rational exponents to simplify expressions that we have. Okay? So if we have the nth root of some number a, right, and n is greater than or equal to 2, right, so it's at least a square root, then we have this formula right here. So all we're saying here with this formula is that if we have the nth root, that's the same thing as saying that we have the nth root. That's the same thing as saying that we have 1 over n as the exponent. We have 1 over n as the exponent. Okay. So we can use that property to simplify some of these examples, right? So if we have this first one, and it says, hey, let's rewrite this in radical notation. So we want it like this. This is our radical notation. And we want to write this, so we'll start with a in radical notation. Well, when we have this 1/5, remember we can distribute this to each one of the factors in this parentheses, right? So we're going to have 3 to the 1/5 power. We'll have x to the 1/5 power. And then y, we'll have y to the 4th. Oops. Y to the 4th, and that's multiplied by 1 over 5. Okay, so 3 to the 1/5 power is just the 5th root of 3 multiplied by the 5th root of x multiplied by, and notice that we have this 1/5 power, so that's going to be our 5th root still, right? But that's just y to the 4th power, and that's to the 5th root. Okay? Or you could also write it as, so similarly, if you wanted to multiply those together, it could be y to the 4/5 power. Oops, y to the 4/5 power. Okay. Okay. B says we have 100 to the 1/2 power. So since it's to the 1/2 power, that's just the square root. So we have the square root of 100. And since it's even, right, n is even here, it has to be non-negative. So we have to have the absolute value of 100, which is 10. We need the absolute value. Okay. And then C, this is just the cube root of negative 64. So this is the cube root of negative 64. And the question is, what multiplies by itself 3 times to get to a negative 64? Well, I know that 4 multiplies by itself 3 times to get to a positive 64. So we just need negative 4. Okay. And since this is an odd root, it can be any real number. Right? So since it's an odd root, it can be any real number. It doesn't have to be only positive. Okay. So we'll move on. We'll try 2 more here. So this one says rewrite with rational exponent. So we're going to go backwards. So instead of having a rational exponent, we're given the radical and we have to change it into a rational exponent. So if we have the 5th root, that's just the same thing as saying something's to the 1/5 power. So we have 13x raised to the 1/5 power. The 1/5 power. Okay. Then on this one, we have x to the 5th. And that's square rooted. So if it's square rooted, is raised to the 1/2 power. So you have x to the 5th. Oops. X to the 5th raised to the 1/2 power. Okay. And when we have a power raised to another power, that's when we multiply them together. So this is the same thing, but this is equivalent to x to the 5/2, or 5/2 power. Okay. So we've dealt with those. We've gone forwards and backwards with that. So let's move on to the next thing. So if we have something to the nth root, and this represents a real number, m over n. I think so m over n is a positive rational number reduced to lowest terms, and n is greater than 2, then we have this rule. So basically all this is saying is that we have this rule right here. So if we have a to the m divided by n power, that's the same thing as saying we just have the nth root of a, and all of that is raised to the nth power. Okay? But we can also look at it the other way. We can say, well, we can take the exponent for the m to a, and then we can take the nth root. So we can go either way with this. Okay. Okay. So we can use those new rules to rewrite each of these in radical notation. Okay. So I think for a, I'm going to use the first rule. So I'm going to use rule 1 here. I'm going to use rule 1 for this. So that means that my division, whatever I'm dividing by in my exponent, that's going to be on the inside, and then I'm going to raise it to the m power. Okay? So in this case, n is 2 and m is 3, right? So on the inside, I'm going to have a, which is 25, to the nth root, right, which is 2 in this case, so that's just a square root. And then I'm going to raise that to the third power. Okay? Now remember, since we're taking the square root of something, we have to only take the positive case, right? So the square root of 25 is a positive 5, and that's to the third power still. And 5 times itself 3 times is 125. Okay, easy enough. Now the question is, what should I use for the rule for b? And I think that I can use the same rule again. So I'm going to use rule number 1. Okay? So rule number 1 says we have a negative 27. We take the third root in this case of it, the third root, and then we raise that all to the second power. So the third root of a negative 27 should be a negative 3. So we have negative 3, and that's still squared. Okay. Negative 3 squared, so that's negative 3 times negative 3 is a positive 9. Okay. So most of the time in math, you'll see that first one come up a lot more, but it's the exact same thing as this one. They're both equivalent. Okay, so we will move on to the next part now. The next part, we're going to rewrite these with rational exponents, right? So we're going to go backwards just like we did with the first rule. So this one is saying that we have x to the 4th and we're taking the 7th root. So remember, if we have the 7th root, that's the same thing as raising it to the 1/7 power. So the a is just x to the 4th raised to the 1/7 power, right? And when we have an exponent raised to another exponent, we can multiply those. So we get x to the 4/7 power. Okay. And then that's our rational exponent, right? Okay, we can do the same thing over here. And you should notice very quickly, we have this 11xy, which is our a right in the middle, right? 11xy. That's raised to the third power, and then we take the square root of that, right? So this should just be 3/2, right? Or just 1/2 raised to the third power, right? So maybe I'll add that step in. So it's 11xy raised to the 1/2 power raised to the third power, right? And that's the same thing as that. Okay. So all we're doing there, we're just changing the square root into to the 1/2 power, multiplying 1/2 by 3, and we get 3/2. Okay. All right. Move on to the next part now. So this one's going to be a word problem. So this one says the Galapagos Islands, lying 600 miles west of Ecuador, are famed for their extraordinary wildlife. So we're given a function. So we have function equals, or function of x is equal to 29 multiplied by x raised to the 1/3 power. And it says this models the number of plant species, so that's our f of x, that's the number of plant species, on the various islands of the Galapagos chains in terms of area, so x. So our variable x is our square mileage, so whatever we're looking at of some island. So then it says use the function to solve the following problem. So it says how many species of plants are on the Galapagos Islands that has an area of 27 square miles, right? So that's just what our x is equal to, right? That's what x is equal to. So we know that we have 27 square miles, and we want to know what is this when we have f of 27. Right? So that's equal to 29, substitute in 27 to the 1/3 power. And remember, 27 to the 1/3 power, that's just the cube root of 27, right? That's still multiplied by 29. And 27 is, the cube root of 27 is just 3, right? 3 times 3 times 3. So we have 29 times 3, that's still f of 27, right? And 29 times 3 is 87. 87, right? So our answer to this one is 87. So to answer our question, how many species of plants are there? There's 87. Okay. All right, so now we'll move on to negative rational exponents. Okay. So if we have a to the negative m over n, and that's a real non-zero number, then we have this. So if we have a to some negative exponent, that's the same thing as saying we have 1 over the positive exponent. Okay? So this will work with our whole numbers as well. So if I have a to the negative 2nd power, as an example, that's the same thing as I have 1 over a squared. Okay? So a squared. Okay, so that's all we're saying here is if we have a negative exponent, we just take the reciprocal and then we have the positive exponent. Okay, so for the first example, I have 8 to the negative 1/3 power. So that's the same thing as saying I have 1 over 8 to the 1/3 power. Okay, and 8 to the 1/3 power is the same thing as saying I have 1 over the cube root of 8, right? And the cube root of 8 is 2. So this should be 1/2. Okay, let's look at the next one. So the next one, we have something to the negative 5/9 power. So that's the same thing as saying we have 1 over 3xy to the 5/9 power. Okay. So 1 over 3xy all to the 5/9 power. And if I wanted to change that into radicals, right, I could say, well, this is the same thing as saying I have 1 over the 9th root of 3xy, right? And all that's raised to the 5th power. It's all raised to the 5th power. Okay. All right, so that's good. Let's move on to the next concept here. So we'll talk about a few properties now. So these are some special properties that we have of rational exponents. So this is going to help us solve rational exponent problems. So if m and n are rational exponents, right? So that's just fractional, right? So we could say it's fractional. Same thing, fractional or rational exponents. And b and y, or a and b, are defined as real numbers for which the following expressions are defined, right? So all this is saying is we just have 2 exponents and 2 numbers. So the first one's saying if we're multiplying 2 exponential expressions together and they have the same base, right? So we have the same numbers. then we can just add the exponents, okay? So basically, an example is, if we have maybe 2 to the 5th power multiplied by 2 to the 3rd power, that's the same thing as saying we're just adding the exponents. It's 2 to the 8th power. Okay, and if we're dividing the same base by different exponents, we subtract them, right? So if I have 2 to the 5th divided by 2 to the 3rd, that's the same thing as saying 5 minus 3, so 2 to the 5 minus 3, which is equal to 2 squared. Okay, the third one, if we have a number, it's raised to an exponent, and then that whole thing is raised to another exponent, that's when we multiply them together, right? So just like we've seen on the last page. So we have something raised to another power, we multiply the powers together. Okay, when we have the product of numbers, so not the sums, specifically products, we can distribute the power to both factors, right? So the reason it won't work for sums is because we have something called the distributive property, right? So this is not the same because remember, if we have like something like a plus b squared, right? That's not the same thing. That's not equal to a squared plus b squared, right? We have that middle term in there. We have that middle term 2ab, right? So these are not the same thing. Okay, and then if we have two numbers divided by each other, right, and we have it raised to some power, we can distribute the end to the top and to the bottom. Okay, so you distribute the end of both of them, we get a to the n and b to the n. Okay, so let's look at some examples here. We have this example right here. This one says we have x to the 3/7 power, and we're dividing it by x to the 1/7. So this is just like our division rule, right? So this is going to be our second rule here. So when we're dividing these, and they have the same base, all we need to do is subtract the exponents, right? And remember, the order matters here. So we have to have this exponent first and have the 1/7 second, okay? So I have x to the 3/7 minus 1/7, which is equal to x to the 2/7. Okay, for B, when we're raising something to a power, right, that's going to be our, it's going to be both powers, right? It's going to be rule 3 and rule 4. Right, so we're raising it to a power, so we multiply them, but we have two factors inside, right? So we have to distribute it to both of them. So this is going to be x to the 1/4 multiplied by x to the 1/3, or multiplied by the 1/3 power, right? Then we have y to the negative 2/5 multiplied by 1/3. Right? So this first one, we get what? X to the 1/12 power, and this will be y to the negative 2/15 power. Okay. And then we can do something similar to C, right? So this one, notice we have the same base on the top and we're multiplying them together. So since we're multiplying them together, we can add the exponents, right? So on the top, we'll get 5 to the 3/4 plus 1/2 power. And that's still over 5 to the 1/4. 5 to the 1/4 power. Okay. Add those together, we get what? 5 to the 5/4 power. We get 5 to the 5/4 power. 5/4 power divided by 5 to the 1/4 power. 5 to the 1/4 power, right? And that is equal to, since we have the same base and we're dividing, we subtract the exponents, right? So we have 5 to the 5/4 minus 1/4, which is equal to 5 to the 4/4, right? And 4/4 is just 1, right? So we just have 5 to the first power or just 5. Okay, so that takes care of those three problems, right? So we're just manipulating the equation or the expression to simplify it down so it's easier to understand. Okay, so let's try a few more examples here. So this one's going to be very similar to the last one, right? We're just distributing it and we're distributing it to both of them. And so once we're raising a power to another power, we multiply them. So this is equal to x to the negative 3 over 5 multiplied by 1/3. And then y to the 1/4 power multiplied by 1/3. Right? So we're distributing that 1/3 to both of these. Okay, so here we multiply the tops, multiply the bottoms. We get x to the negative 3 over 15. And we get y to the 1 over 12. Right? These are multiplied together. Okay, simple enough. So let's move on to the next one now. So the next one will be a here. This one we have to do a little bit more work, right? So this one we actually have to convert a little bit. So I'm going to convert this first. When we have something to the sixth root, that's the same thing as raising it to the 1/6 power, right? So I could say, well, hey, this is b squared raised to the 1/6 power. And I can do the same thing on this one, multiplied by a squared b to the 1/3 power, right? Okay, and after I have that, now I can distribute this 1/6 and distribute the 1/3 to each of the factors. So we get a to the 1/6, b to the 2/6 multiplied by a to the 2/3, b to the 1/3, right? And notice we have the same base, right? We have two a's and we have two b's, right? So I'm going to combine the a's together. I'm going to combine the b's together. So if I combine the a's together, we're going to add the exponents, right? So we have a to the 1/6 plus 2/3, right? And then we have b to the 2/6 plus 1/3, right? So a should be a to the 5/6, and we get b to the 2/3 power, right? Or 4/6 if you'd like, either one. And then of course those are just being multiplied together still. Okay, let's look at b. So b we have, it looks like we have 2x, that's to the 3rd root, and then we're taking that answer to the 5th root. So I'm going to convert both of these into fractional exponents. So we have 2x raised to the 1/3 power. Oops. And then that's raised to the 1/5 power. Right? And then notice we have a power, and that's raised to another power. So I can multiply those together. So we get 2x to the 1/15th power. And then we can distribute that to the 2 and the x. We're going to distribute to the x and the 2, right? So this is 2 to the 1/5 power, or 1/15th power rather. And this is x to the 1/15th power. Right? And of course, they're still just being multiplied together. Okay. We have another example here. So we have x to the 3rd power, and then we take the 6th root of that. So this is just x to the 3rd power raised to the 1/6 power, right? When we're raising a power to another power, we multiply them. So we get x to the 3/6 power, right? And that's the same thing as saying it's x to the 1/2 power, right? And if we wanted to change that back to a radical, we could say that's just the square root of x, right? That's the square root of x, right? Any of those last three is correct, right? This is the most simplified, and then this is just changing it back to a radical. Okay. All right, so we'll move on here. So we'll go into 7.3. We're going to talk about product rules for radicals, okay? So if we have the nth root of a and the nth root of b, right, where those are just two numbers, then we have this rule, whereas if we're multiplying them together, that's the same thing as, right, if we're taking the radical and then multiplying, it's the same thing as multiplying them together and then taking the radical. So we can do it in either order. Okay? So the product of two nth roots is the nth root of the products, right? So we can do it either way. Okay, so if I use this first example here, this one says, hey, I have the third root of 5, and I have the third root of 4, right? And I say, hey, I want you to take the third root of this. Well, this is the same thing as saying, take the third root of 20. Right? And notice that we have the third root of 20, right? But I don't think there's any perfect squares, right, in that I can multiply together 3 times by itself. So I can't really pull anything out. So that should be simplified as is for A. If I look at B, notice that we have x minus 5 as one of them, and we have x minus 5 to the 4th. So that's the same thing as saying, well, we have the 6th root of x minus 5 multiplied by x minus 5 to the 4th, right? And x minus 5 multiplied by x minus 5 to the 4th, well, notice that they have the same base, right? And this is to the first power, so we can add the exponents. So this is the same thing as saying we have the 6th root of x minus 5 to the 5th power. Okay. All right, so we'll move on here. So if I take my next one, so this one, they have the same radical, right? They're both to the 7th root. So that means I can multiply these together. So I can take the 7th root, of 2x multiplied by 6x to the 3rd. I'm taking the 7th root. And that's just equal to, well, 2 times 6 is 12. So I'm still under the 7th root. Well, this is 12. We have x and x to the 3rd. That's x to the 4th. Okay, simple enough. What if I have something a little bit more complicated? So this one, we'll have to kind of use our tools that we've learned before about factoring. So if we have a radical expression whose index is n, right? So our index is just this nth power thing up here, right? That's just our index. Whose index is simplified when the radicand has no factors that are perfect nth powers. Okay, so it says to simplify, the only thing we need to do, we need to write the radical as the product of the two factors, right? So we're just simplifying as much as we can, just like we did before. And then we'll use the product rule to take the nth root of each factor, and then find the nth root if there's a perfect nth power. Okay. Okay. So as an example, notice that on the first one here on A, when we're trying to simplify this, we're taking the square root of 28. So what we want to do is see if there's any factors of 28 that are perfect squares, right? So in this case, we need a perfect square. Well, notice that 28 is a factor of 4 and 7, right? So if I want to split these apart, I could say this is the square root of 4 times 7, right? Of 4 times 7. And then notice that 4 times 7 is the same thing as the square root of 4 multiplied by the square root of 7, right? We can split those apart. Those are one of our rules, right? And the square root of 4 is just 2, right? So that's 2 square root of 7. So these are the same thing. We just took all the perfect squares that we could out of the problem. Okay. So let's look and see if we can do that for this one up here. So notice that I can split this up. I can say, well, this is the third root of negative 32. Negative 32 multiplied by the third root of x squared multiplied by the third root of y to the third. Of y to the third. Right. it's just a 3 up there. Okay. So notice that this one, y to the third, and then we take the third root. Well, that's just going to be y, right? So that'll just be y. When we have x squared to the third root, well, that's the same thing as saying we have x to the 2/3 power, right? And notice this negative 32, we have a factor of negative 8 and a positive 4, right? And negative 8, the third root of that is just a negative 2, right? So this turns into a negative 2, and we still have the third root of 4, right? So our final answer here is these 3 strung together, right? So I could also write it as, if I wanted to kind of leave this x in this notation, we could say, well, we have negative 2y, and that's to the third root of 4x squared, right? So if I wanted to just leave that in the third root. So that's also a final answer. Okay. All right, let's try some more. So this one, we have a function of x, right? And what I'm going to do is I'm going to split this up. I'm going to split the 48 up into one of them and split the x minus 2 to the third power into another one, right? So we have the third root of 48, and that's multiplied by the third root of x minus 2 to the third power, right? And notice the third power and the third root will cancel, so we'll just get x minus 2 here. So we just get x minus 2 here. And then the question is, do we have any perfect squares in 48, right? So if I think the only thing that might be possible is like something like 2 or 3 to come out of it, right? So notice that this, I know that 8, the third root of 8 is 2. So the question is there anything multiplied by 8 that could go into 48, or 2 things multiplied together that go into 48, right? And that's just 8 and 6. So if I take the third root of 8, that's 2. The third root of 6, we'll just keep it as that, the third root of 6. And that's multiplied by x minus 2, right? Okay. So that one was still pretty simple, right? So we just kind of have to factor it out and take any perfect squares that we can. Okay. All right, so we'll move on to the next one then. So when I want to simplify things, and notice that we've already seen this rule before, but we're just restating it here. So for any non-negative real number a, if we have something to the nth power and we're taking the nth root, right? So just like this up here, right? So just like that, then those just cancel out and we're just left with a. Okay. Okay. So let's look at what we have here. So I'm going to say, if we have 40 multiplied by x to the third, and we're taking the square root of that, well, I know 40 is the same thing as 4 times 10, right? So the square root of 4 is 2. The square root of 10, I'm just going to leave it as the square root of 10. Okay. But notice this x to the third. We can split that into factors too. We can have that x squared multiplied by x, right? And that's still the same thing. So notice that if I have that, well, this is just we have the square root still, right? So I'll just leave it as x squared multiplied by x. And notice the square root of x squared is just x, right? So this is 2x square root of 10x, right? So we're kind of splitting the factors off into those square roots so we can simplify it, right? So we can do the same thing on the next one. So we can take the fourth root of 96, right? And the fourth root of 96, that's going to be what? 16 times something? 16 times maybe 6. Let me check really quick. 16 times 6. Yeah, 16 times 6, right? And the reason I guessed it might be that is because 2 to the 4th power is 16, right? And then if I notice this x to the 11th over here, so this is the same thing as saying, well, maybe I have an x to the 8th power, right? And that's multiplied by x to the 3rd. And the reason I'm doing that is because if I have x to the 8th power to the 4th root, that's just x squared, right? So this will turn into 2. So that'll be 2 multiplied by x squared multiplied by the 4th root of 6x to the 3rd, right? So we're just doing the same thing that we've done earlier where we're kind of splitting it up and see what factors evenly or really nicely out of these equations or these expressions. Okay. So we can do the same thing on the next one, right? So this is going to be the same thing, but notice that we might have something that factors really nicely here, right? Because we have the square root and we have this x to the x squared, right? So let's try. Let's still have the square root here, but let's try to factor this, right? So when I try to factor this, and maybe you'll find it out here in just a second. Let me see if I can factor it here. So we have, what, 3x squared minus 12x plus 12. And notice we're trying to factor it into two different things, right? Well, one thing that I notice, so maybe I actually went a little bit further ahead. One thing I notice is that I can actually factor out a 3 out of everything, right? So let's factor out a 3. So I'm going to factor out a 3 out of everything. Oops. Factor out a 3. So let's factor out a 3 out of everything, and we get x squared minus 4x plus 4. And that's a lot easier to factor, right? So the reason it's a lot easier to factor is because we have a 1 for our coefficient, right? So my question is, what multiplies to a positive 4 and adds to a negative 4, right? Because we're going to factor this. So we're going to have the square root of 3, and then we have x's at the start, right? X and x. And I noticed that it's negative 2, right? So negative 2 plus negative 2 is a negative 4, and it multiplies to a positive 4. Well, notice I have 2 of the same factors, right? I have an x minus 2 and an x minus 2. So that's the same thing as saying, well, I have the square root of 3 multiplied by x minus 2 squared. And then notice we have a square root and a square, right? So if I have a square root and a square, those will cancel. So we have x minus 2 multiplied by the square root of 3, right? Okay. All right. So that's it for that problem. We'll move on here. And we'll do this one. So this one, we're going to try to find those perfect squares, right? So notice the first one is the same thing as x to the 8th multiplied by x. This one's y to the 10th multiplied by y. And then we have multiplied by z squared multiplied by z, right? That's all square rooted still. And the reason I'm doing it like that is because this x squared factors really nicely into a square root, right? So if it's x to the 8th, we distribute this square, right, or this 1/2 power, the square root over the 1/2 power. So that'd be 8 over 2, or x to the 4th. Y is 10 divided by 2, which is y to the 5th. And then z squared, square root is just z. And then we have the square root of x, y, z. Right? So we're just factoring out those squares. Okay, let's go on to the next problem here. So we're going to do something very similar again, right? So I noticed that I have the 4th root on both of these, right? So since I have the 4th root on both of these, I can use my rules and combine those, right? So I can say, hey, I have the 4th root of everything in here multiplied by everything over here. So I have 8 times 4, which is 32, right? X squared multiplied by x to the 4th is x to the 6th. y to the third multiplied by y is y to the fourth. Z to the third multiplied by z to the sixth is z to the ninth. Right? And then now I can take the fourth root of things. So notice that this factors into 16 and 2. This factors into x to the fourth, x squared. This factors to nothing, right? It's just y to the fourth, so we just leave that. And this factors into z to the eighth multiplied by z. The fourth root of 16 is 2. X to the fourth is, to the fourth root is just x, right? Y to the fourth root is just y. Z to the eighth to the fourth root is z squared. And then we still need the fourth root for everything that's left over, right? So we have a 2, an x squared, and a z, right? Okay. Okay, let's do the same thing for b here. So this one, we're taking the fifth root, right? So we have 8 times 8, which is 64. So this is the fifth root, 64. The x's combined, we get x to the fifth. Y's combined, y to the 12th. And then the z's combined together, and we get z to the 11th. Oops. Z to the 11th. Right? So now we can simplify, right? So 64 is what? 32 times 2? 32 times 2. Right? And 32 to the fifth root is going to be 2. X to the fifth root is just x. Y to the 12th is the same thing as y squared, or y to the 10th rather, multiplied by y squared. Y to the 10th to the fifth root is y squared. And then z to the 11th splits off into z and z to the 10th, right? Z to the 10th to the fifth root is z squared. And then to the fifth root, so everything we have left over, we have a 2, a y squared, and a z. Okay. All right, so we'll move on here. And we'll actually move on to 7.4. So 7.4, we're going to be doing very similar stuff to what we've done before, but we're just kind of building on top of it, right? So we're just dealing with radicals again. So when we have 2 or more radical expressions that have the same indices, right, or the same root or whatever that you're taking, right, they're called like radicals. So like radicals can be combined under addition in the same way that like terms can be combined under addition, right? So as an example, if we have like 3x plus 2x, right, we can combine those together to 5x, right? So notice this variable here, this x, it's just like saying we have 3 square roots of 2, and we're adding together 2 square roots of 2, right? So that's just 5 square roots of 2. Right, so we're just doing the exact same thing that we've done before with variables, but we're doing it with radicals this time, okay? So if I have 9 cube roots of 3, and I'm subtracting 4 cube roots of 3, I just have 5 cube roots of 3 left, or cube roots of 7, sorry. Right, so we're just subtracting the numbers in front. Okay, on B, notice that we have 6 square root of 7 and 2 square root of 7, right? And those are both positive, so we can add those together. So we get 8 square root of 7. And then we have a negative cube root of 3 and a positive 5 cube root of x, right? So if I take those, we get what? A positive 4 cube root of x. Oops, cube root of x. We're just combining our like terms. And remember, we can use the commutative property to move those around and combine them together, right? All right, so we'll move on here. We have 2 more problems here. So notice that we have 2 things, and they don't look like they're similar right now, but we can change them a little bit, right? So notice that this first one, they have a common factor of 4 between the both of them. So let's take out a 4. And now we have x minus 3, right? We're adding that to the square root of x minus 3. Now notice we have an x minus 3 in both of them, right? And notice that we have a problem here, though. We have the square root of 4. Well, the square root of 4 is just 2, right? So this is the same thing as saying, well, we have 2 square root of x minus 3. And we're adding to that the square root of x minus 3. Right? Well, we can just combine those together, and that just means that we have 3 square roots of x minus 3. Okay, let's look at b now. So b, we have 4 multiplied by the cube root of x to the 4th y squared, and plus 5x cube root of x multiplied by y squared. So notice that we can split this x factor here into x to the 3rd and x. And then notice that we have this x to the 3rd cube. So we can take that out, right? So x to the 3rd cube rooted is just x. So we get 4x. And then in the parenthesis, or in the square root, we still have, or cube root, we still have x y squared. And we're adding to that 5x cube root of xy squared. Okay, so now that we have that, we can combine our like terms. So we have 4x here and 5x here, so that's 9x. And then multiplied by the cube root of xy squared. Okay. All right. Let's move on to our next page now. So we'll do the quotient rule now, right? So this is just the opposite of the multiplication rule, the product rule we just did, right? Okay, so if we have a to the nth root and b to the nth root, well, if we have the nth root of a and b, we can distribute the nth root to the top and to the bottom, right? So just like we did with our exponents before, where we had something to the nth power, and we had a division or a fraction, right? We could distribute that exponent to the top and the bottom, right? So if I wanted to illustrate this more, we could say, well, we have a over b, right? So just rewriting what we had over here. And this is to the 1 over n power, right? Because we have the root. So this is the same thing as saying, well, hey, I have this exponent, so I can distribute it to the top and the bottom. This is equal to a to the 1 over n divided by b to the 1 over n. And that'll help us simplify some expressions that we might find, okay? Okay, so this one says simplify this. So I have the square root of 50x to the 3rd divided by 81y to the 8th. So to simplify this, I'm going to take the square root of the top and take the square root of the bottom. So we have 50x to the 3rd, square rooted, over the square root of 81, 81 y to the 8th. Okay. So now that I've done that, what I can do is I can just take the square root of the top, right? So the square root of 50, well, I know that's 25 times 2, right? And the square root of 25 is 5. So on the top we get 5. X to the 3rd square rooted is what? X. We can split this into what? X squared and x. So we'll take the square root of x squared, which is just x. That's where I got that from. And then we have the square root of, we still have a 2 left over and an x, right? Over the square root of 81 is 9. The square root of y to the 8th is y to the 4th power. Y to the 4th power. Okay. Now we can do the same thing with b, right? So I can take the 4th root of the top, the 4th root of the bottom. So if I take the 4th root of the top, notice that y factors into y to the 4th, y to the 3rd. So the 4th root of y to the 4th is just y. So we get y, 4th root of 13 multiplied by y to the 3rd over, remember the 4th root of x to the 12th is just going to be x to the 3rd. to the third. Okay, so that takes care of those two problems. We'll move on here. So this one, it looks like we're simplifying again, right? But notice we have the square root on both of them. And I don't really see anything that's maybe that nice that we want to take the square root of. So I think what I'm going to do is I'm just going to combine these for A and say, hey, I'm going to take the square root of the whole thing. So we got 54, a to the 7th, b to the 11th, over 3a to the negative 4th, b to the negative 2nd. Okay? So 54 divided by 3, we get what, 18? So we get 18 when we divide our coefficients, so 18. Remember when we have some exponent divided by another one with the same base, we subtract the exponents, right? So we have 7 minus a negative 4. So a to the 7th minus a negative 4. And then same thing with b, we have b to the 11th minus a negative 2. That's all square rooted still. So 18 is, let's see. So I don't think 18 can be simplified at all with a square root. So I'm just going to leave it as the square root of 18. But notice that we have a to the 7 minus a negative 4, which is a to the 11th. So we can change this into a to the 10th a multiplied by a. And we can change b into b to the 12th multiplied by b, right? So this will simplify to a to the 5th, b to the 6th, square root of 18ab. Okay. All right, and I can do the same thing with the other one, right? So we can say, let's combine this so we have the cube root of everything, and then we'll combine our like terms. So we have 250 divided by 2, which is 125. This is the cube root of 125. The x's, we'll just have x squared, right? Because we subtract the exponents. And we just have a y to the third still. Okay. The cube root of 125 is 5. The cube root of x squared is still just the cube root of x squared. And the cube root of y to the third is just y. Okay. And we still just have the cube root of x squared. Okay. All right, simple enough, right? So we're just combining the cube root on the top and the bottom to simplify what's inside first. Okay. Then we'll move on to the last one here, for this page at least. So we'll combine the square roots. So we get the square root of 40x to the 5th over 2x. 40 divided by 2 is 20. Subtract the exponents, that's x to the 4th. Notice that 20 splits into 5 and 4. The square root of 4 is 2. So we get 2 square root of 5 still, right? So we still have the square root of 5. X to the 4th square root is just x squared. It's the square root of 5, right? So we're just simplifying what terms we can. Okay. All right, we'll move on here. Actually, that's the end. That's the last one. Okay. Does anybody have any questions so far? Or any questions on the notes? Okay. If you don't have any questions on the notes or anything, you're free to go. I'll do kind of like a review session. Oh, there we go. We have something. I'll do a little bit of a review session on Thursday. Okay, cool.